to SH mean, with perforations in the direction of SH max. Similar closed form expressions can be derived for any well trajectory and perforation direction. When we plot those two fracturing stresses against the wellbore pressure, which by the assumption I mentioned earlier is equal to the perforation pressure, we see the red longitudinal fracturing stress starting from a highly compressive value, becoming more and more tensile as wellbore pressure increases, whereas the blue transverse fracturing stress begins from a small tensile value and slowly becomes more tensile at a rate much smaller. This creates an intersection point which indicates what I call the breakdown pressure window for transverse fracture initiation. This means that if the breakdown pressure, which is the highest pressure reached during a hydraulic fracture treatment, is within this yellow shaded region, transverse fracture initiation would be created, because in this region the transverse fracturing stress is tensile and is more tensile than the longitudinal fracturing stress. Remember, hydraulic fractures are tensile failures. If, however, the breakdown pressure is higher outside this region, longitudinal fracture initiation will be created because the longitudinal fracturing stress is more tensile. This breakdown pressure window constraint is very important because there are parameters controlled by the practitioner on the surface that can influence the magnitude of the breakdown pressure downhole. For instance, it has been proven that low pressurization rates can suppress the breakdown pressure for a given in situ state. Therefore, strategic use of low injection rates can be employed to create an environment where transverse fracture initiation would be promoted. The range of stress states which can occur in the Earth's subsurface can be visualized in a very simple two-dimensional plot called the allowable stress state diagram, or map. This has SH max normalized by SV on the y-axis and SH mean normalized by SV on the x. The dotted diagonal represents the line of horizontal isotropy where SH max is equal to SH mean, and the solid dark lines are drawn using this relationship here and represent the frictional limits for friction factor 0.6 and 0.8. Any stress state outside those bounds is virtually unstable and cannot occur because if a fault exists under those stress state conditions, it will automatically fail in shear. There will be fault slippage, which is basically an earthquake. I took this plot and added two lines to it. The cyan line for the stress state for which the axial stress is equal to 0, showing the limits, and the green line for the stress states for which the axial and tangential stresses are equal to each other. The blue region behind both of those lines indicates the range of stress states in which transverse drilling induced tensile fractures will be promoted. We can see from the graph that the overwhelming majority is red, indicating longitudinal drilling induced fractures. Now, if we add a third line on the plot, the magenta line, for the value of SH mean given to us by league of testing data, as I mentioned earlier, we can now create a smaller yellow triangle within the blue region, which indicates the range of stress states possible for the for the in situ stress state if transverse drilling-induced tensile fractures are observed. Then we only need to take the vertical extent of the triangle and read from the y-axis the range of magnitude for SH max. If longitudinal drilling-induced tensile fractures are observed, the range or ranges at which we can constrain SH max is not as narrow as for transverse, because transverse is rarer. However, it can still be useful because it still constrains SH max to a narrower range than what the friction factors on their own can do. For completion-induced hydraulic fractures, using this same graphical method, the cyan line becomes the line indicating the stress states at which the transverse fracturing stress is equal to 0, and the green line the range of the stress states for which the transverse and longitudinal fracturing stresses are equal to each other. From the diagram, visually, we can see that the blue region now is bigger than before during drilling. And this on its own allows us to conclude that the presence of perforation tunnels per se aid transverse fracture initiation. We also see that the impact of the Biot's poroelastic coefficient, which impacts only the cyan line, is extremely minor. Nevertheless, the red region is still the overwhelming majority. This suggests that under most stress states, the fracture initiation taking place is longitudinal to the wellbore, and non-preferred perforation plane orientation, which is therefore unstable. This implies that as the fracture propagates away from the wellbore, reorientation will take place to align the fracture with the preferred fracture plane, which is given to us by Hubbard and Willis, and for this well configuration is transverse to the wellbore. This reorientation from longitudinal fracture initiation to transverse final propagation plane generates fluid tortuosities in the near wellbore region, which triggers serious completion-related problems such as early screen-outs and fracturing fluid leakage across stages during a multi-stage treatment. As we see here in this schematic, showing the results of a tracer test run during a multi-stage treatment, we see yellow fluid from the first stage appearing in stages 2 and 3, despite those stages being isolated from each other using packers. The same thing can be said for red fluid from the second stage appearing in adjacent stages, same for blue fluid from the third. This decreases the overall efficiency of the hydraulic fracture treatment and leads to production-related problems such as poor well performance after stimulation, with an adverse impact on the net present value of the overall stimulation treatment. As mentioned earlier, the perforation direction is an independent variable in our analysis shown to control the orientation of fracture initiation. As we change the perforation direction from top of the hole, one extreme, 0 degrees, to side of the hole, which is another extreme, 90 degrees, the breakdown pressure window varies. In our papers, we call the perforation direction in which the breakdown pressure window is maximized as the preferred perforation alignment, or PPA. PPA solely depends on the in situ stress regime local to the well in question. For normal faulting stress states, like the Barnett shale, for example, the preferred perforation alignment for a horizontal well drilled parallel to SH mean, which is the best orientation for achieving transverse fracture initiation, which is our main objective, is on the side of the hole, parallel to SH max. For strike slip faulting stress regimes like the Marcellus shale, the PPA is on top of the hole parallel to SV. This provides justification for using an oriented perforation strategy where perforations of only a single face angle is used in order to maximize the chances of achieving transverse fracture initiation. This assumes that there will be no leakage around the wellbore, which can really be a deal breaker in this case. For reference, on the right side, on the plot on the right side, I show an allowable stress state diagram with the stress states of 7 prolific shale plays on which we perform case studies, the results of which will be shown in the next section. 5 of those, the Barnett, Bakken, Fatesville, Haynesville, Niobrara, are normal faulting stress states, and 2 of them, the Marcellus shale and Vaca Muerta shale from Argentina, are strike slip fault regimes. In conclusion for this topic, analytical orientation criteria were derived for fractures initiating from perforated and not perforated wells, and breakdown pressure window is found to exist controlling transverse fracture initiation. The range of breakdown pressure window is maximized for perforations parallel to the preferred perforation alignment. Longitudinal fracture initiation is shown to be a frequent occurrence for horizontal wells, leading to serious completion and production related problems observed in the oil field.